What's up, AP Physics C Mechanics students? Welcome back to our elegant physics videos. Today's topic, 5.1, rotational kinematics. So let's jump right in. Variables of circular motion. In Unit 2, we have discussed and developed the kinematics of circular motion. The kinematics are dictated by the following variables of motion. The variable of motion, the angular position, the symbol is theta, the unit is radian. The angular velocity or angular frequency, the symbol is omega, and the unit is radian per second. The angular acceleration, the symbol is alpha, and the unit is radian per second squared. Now, another common unit for the angular position, or let's say the angular displacement, we know that the angular displacement can be written as delta theta is equal theta final minus theta initial. This is the angular displacement. Now, the angular displacement can be expressed using revolution. Now, what I mean by revolution is the number of completed cycles. So, for example, if we have one revolution, so after we complete one cycle, the angular displacement will be 2 pi. So for every one revolution, for every one completed cycle, the equivalent angle will be 2 pi. Now, to convert it from revolution to radian, we just multiply by 2 pi. Now, another way to express the angular displacement is by use another type of measurement, which is degree. To convert it from degree to radian, we multiply by pi over 180. Now, the common way in this unit to express the angular position, angular velocity, and angular acceleration is by using radian per second, and radian per second squared. So whenever we have the quantity expressed in revolution or degree, we should convert it into radian, and this is how we do the conversion. Now, for the angular velocity, sometimes the angular velocity will be expressed in revolution per second. To convert it into radian per second, we just multiply by 2 pi. If this is written as revolution per minute, to convert the revolution per minute into radian per second, we multiply by pi over, or 2 pi over 60. 2 pi to convert the revolution into radian, and the 60 to convert the minute into second. However, we can simplify it more. So from now on, we can use pi over 30 instead of 2 pi over 60. Also, the distance traveled after we complete one revolution, the distance can be calculated via this formula, r times theta. After one revolution, the measured angle will be 2 pi. So S is equal R times 2 pi, which means the distance traveled after one complete cycle, it will be 2 pi R. Now this 2 pi R is known as the circumference of the circle. And this is how we calculate the circumference of the circle, or the distance traveled after we completed one full cycle. The default positive direction associated with the circular motion is the anti-clockwise. So we consider the anti-clockwise or the counterclockwise to be the positive direction. And for sure, the negative direction will be clockwise. These quantities are best understood when introduced in analogy with rectilinear motion. In the rectilinear motion, we have defined the position to be x, the velocity to be v, and the acceleration to be a. Now, the equivalent position in the circular motion or the rotational motion is the angular position theta. The equivalent to the velocity is the angular velocity omega. And for the acceleration, the linear acceleration, we have the angular acceleration alpha. The set of variables theta, omega, alpha can be related to each other via two different approaches. Via calculus, so we know that the derivative of angular position is the angular velocity. The derivative of the angular velocity will be the angular acceleration. Now, if we move backward, so we will use the antiderivative or the integration. The integral of angular acceleration will give me the angular velocity, and the integral of angular velocity will give me the angular position. And also, we can relate angular position to angular velocity with angular acceleration via the type of motion. So technically, we have two types of motion. The first type is the uniform circular motion, And the second type is the uniform varied circular motion. In the uniform circular motion, the rotation will be with constant speed, and we will describe the motion via only one equation, theta is equal theta 0 plus omega t. Now, for the uniform varied motion, the rotation with constant acceleration and the speed is varied. To find the speed, we just use this equation, omega is equal omega 0 plus alpha t. The theta can be written in quadratic form. Theta is equal theta 0 plus omega t plus half at squared. And the time-independent equation, omega squared is equal omega 0 squared plus 2 alpha delta theta. And finally, delta theta is equal half omega plus omega 0 t. Now, let me pay your attention that we always usually use this version of this for this equation. So we move that theta 0 to the right hand side, and it becomes theta minus theta 0. Theta minus theta 0 is technically the delta theta. So we can write delta theta is equal omega t. Also here, we can reduce it in this form. Let me make some space. So actually, we know that the theta is equal theta minus theta 0. By moving theta 0 to the other hand side, it becomes theta minus theta 0. So we can write it as delta theta is equal omega t. Also here, if you move theta to the other hand side, it becomes theta minus theta 0, which means delta theta is equal omega 0 t plus half a t squared or alpha t squared. Now, also here, that they are already done. So delta theta here, delta theta there. Now, apart from that, we have seen a connection between linear and circular motion. An object M moves along a circle of radius r. Now, the polar coordinates are given by r and theta, and the connection is given by s is equal r theta, v is equal r omega, tangential acceleration is equal r alpha, and the centripetal acceleration will be v squared over r. Consider an object speeding up along a circle. Let's review this uh, case. So if it's speeding up, the velocity will indicate the direction of motion. The velocity always tangent to the path. The centripetal acceleration will be inward, and the tangential acceleration is the quantity that's responsible to increase or decrease the speed. To increase the speed, we set the tangential acceleration within the direction of velocity. So it's going to be tangent to the path and have the same direction as the velocity. Now, as a result, the acceleration vector will be represented by drawing a diagonal vector to the rectangular shape formed by AT and AC. Now, if the object is going down, then the velocity will indicate the direction of motion. The direction of motion is clockwise, so the velocity will be in this way. The centripetal acceleration is always toward the center. But this time, to slow down the object, we must apply the tangential acceleration opposite to the direction of the velocity. Now, this time, after we complete the rectangular shape, the diagonal of this rectangular shape formed by AT and AC will represent the acceleration factor A. Now, what is the difference between V and omega? V is the linear speed of specified point on a rotating disk. So it's a linear speed. It's more about the covering the distance at a specific time. Omega is the angular velocity, which represents how fast the disk is spinning. So for example, here the red gear is spinning more than the green gear. And we can deduce that they have the same linear speed because they are traveling the same distance, but the way of the rotation is different, which means we have different omega. Here also, the speed of the spinning in the smaller gear is less than the speed of spinning in the bigger gear. The distance traveled associated with the belt and the distance during the equal time intervals is the same for this gear and that gear, which means the linear speed is equal in both gears, but the rotation or the spinning, this is different in the smaller gear. The smaller gear is spinning faster than the bigger gear, which means we have here more angular velocity, higher angular velocity than the bigger gear. So same linear speed, different angular velocity. Now here we have different linear speeds at different points on the disk, but the same angular speed for points that aligned on the same line. Now, exercise 1, a disk is free to rotate about an axis perpendicular to the disk through its center. If the disk starts from rest, so we are assuming here that the omega 0 is equal to 0, and accelerate uniformly at a rate of 3 radian per second, so alpha is equal to 3 radian per second squared, and for 4 seconds, it's angular displacement, so we need to find the delta theta. Now, since the acceleration here is uniform, so the type of motion will be uniform circular valid motion, and we can use the kinematic to solve this problem. Now, the delta theta in this case will be given by omega 0 t plus half at squared plus half alpha t squared. So omega 0 is 0 because we have started from rest minus plus, sorry, half alpha t squared. This is the delta theta, and the delta theta can be written as alpha is 3, 4 seconds, and the answer is 24 radian per second. So the correct answer will be D. Now, exercise 2. A rotating platform with a radius 2 meters, so this is R, makes one complete turn, so one revolution every 3 seconds. So every 3 seconds, the object will be able to complete one revolution. Let me remind you that this time is a special time since it's measured for one complete turn. So this can be set it as the period because as according to the definition, the period is the time needed to complete one cycle or one turn or one revolution. However, I'm not going to use this information. Now, the angular velocity of the platform is most nearly, we need to find the velocity. To find the velocity first, let me remind you here that the speed is constant because we are repeating the same process over and over again every 3 seconds. Let first, whenever we have number set it for expressing revolution, we should convert it directly into radian. And we know how to do that from revolution to radian. We multiply by 2 pi. So actually this is 2 pi. And this represents the delta theta, the angular displacement. Now, since the type of motion here is constant circular motion, and then the omega is constant, and we can use delta theta equals omega t. Now, omega is not given. We are looking for omega. So omega is equal delta theta over t. Delta t, delta theta, not delta omega, delta theta over t. Delta theta is given by 2 pi, and the time is 3 seconds. So the final answer would be 2.09 radian per second or 2.1 radian per second. So the correct answer is A. Exercise 3. A disk initially rotating 5 radian per second, so this is the initial velocity, experiences a constant torque. Now, we're going to study torque later, but you can consider it as something equivalent to force. It's equivalent. It's not force, something equivalent to force, and it's necessary here in the rotational motion. Anyway, we don't need it now. We just need the variables. We are studying the kinematics, not the dynamics. So the time here is 4 seconds. That results in an angular acceleration 2 radian per second squared. This is alpha. We need to find the angular displacement after 4 seconds, so delta theta. Now, since we have time, alpha and omega 0, the best way to find the angular displacement is by applying the quadratic relationship. Delta theta is equal omega 0 t plus half at squared, or plus half alpha t squared. Now, omega 0 is given by 5, the time is 4, half the acceleration or angular acceleration is 2, and the time is 4 to the power 2. Plugging this in the calculator, and the delta theta or the angular displacement will be 56 radian. And the correct answer is A. A rotating object has an angular position represented by theta is equal. So theta here is written in the quadratic form, and we know this exactly the same as this equation, theta 0 plus omega 0 t plus half a t squared, or alpha t squared. Where A, B, and C are constant, the student wants to represent a different rotating object that has twice the angular speed at every moment. So we need to increase the speed, or we want to represent a different rotating object that has twice angular speed every moment. So every moment the speed will increase by double. What will be the change that we should make to this equation in order uh, to represent the theta for this case? So what are the changes that we should make here to this equation? So the student can use this equation to find the theta. Now, actually here, in order to increase the speed, we need to activate the angular acceleration because we want to double the speed every moment. So every time the speed will increase by 2. So we need to change the alpha. And the alpha actually, it appears in the third term and the quadratic one. And we know that if you want to double the speed, it means, or we want to change the speed to double, changing the speed every second, it's equivalent to alpha. So by changing the speed every time, we need to change actually the alpha. If you want to double the change, you need to double the alpha. So actually we need to double the step. And as a result, the correct answer would be doubling C all. A wheel of zero point 0.5 radian rolls without slipping on horizontal surface. The axle of the wheel advances at a constant velocity, moving a distance 20 meter in 5 seconds. So 20 meter represent the distance traveled in 5 seconds. And here we have the radius of the wheel. The angular speed of the wheel about its point of contact on the surface is, so we need to find the omega here. So here the object is moving with constant velocity, which means we're going to use this equation to solve the problem. Since we are looking for omega, then we will move time to the other hand side and it becomes delta theta over time. Now, the problem here, we don't know what is delta theta, but we know the distance traveled in 5 seconds. Now, actually, the delta theta is related to the distance. So the angular displacement is related to the distance traveled via this equation. S is equal R delta theta, which means if you want to find delta theta, we just apply S over R. Now, the distance traveled is 20 and the radius is 0.5, which means the angle is 40 radian. Now, we use 40 radian here in the previous equation. We divide over time, which is 5, and the final answer is 8 radian per second. So this is the omega, and the omega is 8 radian dot second squared, second to the power minus 1, or per second. The turntable that is initially at rest is set in a motion with a constant angular acceleration alpha. So the initial velocity is 0, and alpha represents the angular acceleration. And this angular acceleration is constant. What is the angular velocity? We need to find the angular velocity omega of the turntable after it has made one complete revolution. We know that the one complete revolution is equivalent to 2 pi rad, because 2 pi rad represent the delta theta, or the one revolution represent the delta theta or the angular displacement. Now, as we can see here, the time is not mentioned, which means we can use one of the time-independent equation because especially that the angular acceleration is constant. Now we know that the time-independent equation is given by omega squared equals omega squared 0 plus 2 alpha delta theta. Now here they don't want me to find the actual value or the numerical value of the velocity. However, the velocity must be written as an expression in terms of alpha. So we're going to maintain the alpha in our equation, knowing that the object starts from this, which means omega 0 is equal to 0, to alpha multiplied by 2 pi. Now 2 times 2 pi is 4 pi. Now we take the square root to find the omega, and the omega becomes 4 pi alpha. So the correct answer is C. Now exercise 7. A fan blade rotates with angular velocity omega t is equal 1.8 minus 2.2 t squared. The angular acceleration. So here we have the time equation for omega, and we want to find the angular acceleration at specific moment. So first of all, to find the angular acceleration at specific moment, we need to construct the acceleration time equation, and then we substitute the time in this equation to get the alpha, the angular acceleration. We know that the alpha in terms of time can be found by applying the derivative on the omega with respect to time. Now the derivative of the first term, this is constant. The derivative of the constant is 0. The derivative of the quadratic, we just drop the power and we reduce the power by 1. So 2 minus 1 is 1, which means the alpha t is given by minus 2.2 multiplied by 2, it's 4.4. So minus 4.4 times t squared. Now we substitute the time 3 seconds in the equation to get the angular acceleration after 3 seconds minus 4.4 times the 3 to the power 2. And the final answer is minus 13.2 radian per second squared. This is alpha after 3 seconds. And the correct answer is C. A particle moves in the xy plane with the coordinates by x is equal a cosine omega t and y is equal a sine omega t. A is equal 1.5, omega is equal 2 seconds or 2 radian per second. What is the magnitude of acceleration? We know to find the magnitude of acceleration, we simply find it via ax squared plus ay squared, or if we have information about the tangential acceleration and the centripetal acceleration, we use the Pythagorean sum on that. Now, since we have information about the linear position or the Cartesian coordinate system, so one can say that we can use the x to find the vx, and we can use the vx to find the ax. And can be done by applying the derivative. Same thing for y. The derivative of y is vy. The derivative of vy is ay. And then finally, we apply the Pythagorean sum to get the magnitude since we are interested in magnitude. So let's find the Vx. The Vx is the derivative of x with respect to time. Now, this is trigonometric function. We know that the a is just a constant. We place it away. The derivative of cosine is minus sine. And the derivative of the inner function is omega. So we place omega here. So minus a omega sine omega t. Now, the ax is equal the derivative of vx with respect to time. Now, the derivative of vx, this is vx. We place the minus outside. The derivative a and omega are constant or are the coefficient, so we don't apply the derivative on them. We just apply the derivative on the sine and the inner function. The derivative of the sine is cosine. And then the derivative of the inner function is basically omega, because omega t, the derivative of omega t is omega. Now we split omega outside, but we have another omega here, so this will be promoted into omega squared. And this is the ax. Now for the vy, we apply the derivative on the dy dt. Now a sine omega t, the derivative of sine will be cosine, so a remain the same. We split omega outside, and this becomes cosine omega t. And for the ay, it's basically the dvy over dt. Now the derivative of the cosine is minus sine. And don't forget that we're going to split outside the inner function, the derivative of the inner function, the derivative of omega t. This is the inner function is omega. And we have a omega outside. Omega times omega is going to be omega squared. To find the acceleration, we just apply the Pythagorean sum. So it will be equal to cosine omega t to the power 2 plus, and ay is minus a omega squared sine omega t to the power 2. Now we apply the square on minus a omega squared and the cosine, only on the outer function of the trigonometrical one. So the square of the minus is a plus. The square of a and omega squared, I would write it like this. And cosine squared omega t plus, now the square of minus is a plus. The square of a omega squared is a omega squared to the power 2 sine squared omega t. Now I will make some space here. Now we can take omega squared to the power 2 as a common factor. So the acceleration is equal a omega squared as a common factor. And inside we will left with cosine squared omega t plus sine squared omega t. Now we know that cosine squared omega t and sine squared omega t are equal to 1. And 1 times a omega squared to the power 2 is simply a omega squared to the power 2. Now we simply destroy the square with the square root, and the final answer would be a omega squared, which means the correct answer is a is given by 1.5 Omega is given by 2, and the answer is 6 radian per second squared. A windmill is spinning because of the non-uniform force of the wind. So we have a non-uniform force acting on the windmill because of the wind. The windmill is originally spinning at the speed omega zero. This is the original speed or the initial speed. And a crosswind slows it with the angular acceleration of minus omega squared. Now, pay attention to this minus omega squared because the minus a omega squared here um, is due to non-uniform force. When I say non-uniform force is acting on an object, then it will generate non-uniform acceleration. Especially that this omega itself is not constant. We know that A is constant, but the omega is not constant because omega itself is attached to time. It can be written as a function of time. Now we need to know what is the angular speed after t is equal capital T. Now this case is tricky because time is not explicitly written in the expression of alpha. So there is no time here, and especially that the omega is attached to time because this represents the speed at any moment. So therefore, we need to follow a different strategy. This method can be used whenever time is hidden within another quantity. And this method that I will show you to you now is known as the separation of variables. So we can apply separation of variables to solve this problem. Now we know that the alpha is equal minus a omega squared. Remember that omega squared, omega itself, it's written as a function of time. It's not constant, and they didn't mention that. They didn't say the omega in this equation is constant. Now, the technique that I will follow is the separation of variables. So we're gonna unpack alpha in terms of the differential form, which means we're gonna write it like this. Now we're gonna separate the omega from this side and the dt from that side. So we're gonna exchange between omega squared and dt. So it becomes d omega. This is division. It becomes this is multiplication. It becomes division. And this is division, it becomes to the other hand side multiplication. Now, why I didn't apply the integral immediately? The integral requires, on the other hand side, constant value or function in terms of time. I cannot apply the integration with respect to time. Yeah. In other words, I cannot write uh, to find the omega, we integrate alpha dt. I cannot write it in this way if the alpha is not written explicitly in terms of time or if the alpha itself is not written as a constant. So we cannot do that. Whenever inside the alpha there is a function written in terms of time, like omega, then we're going to use the separation method. Now, let me rearrange this equation. So I will write it like this. We're going to drop the d omega next to the omega squared. So it's going to be here. It's equal minus a dt. Now we apply the integration. So we integrate this part and we integrate that part. The minus, you can place it outside or inside, it doesn't matter. Now, the boundaries of the integration on the right-hand side, the variable is t, and we integrate the motion from 0 time to the capital T. So from 0 to capital T. Now, here, the variable is omega. The initial conditions of omega are we started from omega 0, and we end with the final omega, with omega final. So the integration will be different from omega 0 to omega. Remember to link the boundaries of integration with the variables that you have. So always we're going to use the condition, the initial conditions, with respect to this variable. So here the time, the initial condition is 0. And for the variable omega, the initial condition is omega 0. The final time is t, capital T. The final omega is known as omega final. Now, before we start the integration, Let me rewrite this equation again. So it becomes easier to be integrated. We know that 1 over a can be written as a to the power minus 1. And if we have a square here, it becomes minus 2. So 1 over omega squared can be written as omega to the power minus 2 d omega equals minus from 0 to capital T a dt. Now let's integrate omega with respect to the omega. The integration of omega will increase the power of by 1 and we divide over the new power. So if we increase the power by 1, minus 2 plus 1 is minus 1. So omega minus 1 over minus 1. And the boundaries of the integration will be from omega 0 to omega. Now here the integration is much easier because here we have a, which is constant, and we know the integral of constant will be linear. So the integral of a dt, it becomes at. So minus a t, and the boundaries of the integration will be from 0 to t. Now we can rewrite this equation such that we return the omega to the power minus 1 into the denominator, so it becomes a plus. So minus 1, it becomes minus omega 1, and the boundaries of integration omega 0 to omega equals minus a t from 0 to capital T. I will make some space here. Now, if we have minus in the denominator, we can simply write it next to the fraction. So we remove it from the denominator and we place it next to the fraction. So I can write minus 1 over omega, omega 0 equals minus a t 0 to t. Now also the minus can be placed outside. So I will place the minus outside, away from the parentheses. Now we complete the integration. We substitute omega here and then minus omega 0. So minus outside 1 over omega, the final speed, minus 1 over omega 0 equals, we substitute capital T first, minus, we substitute 0. Now we distribute the minus inside, minus 1 over omega plus 1 over omega 0 equals minus 80. And 8 times 0 is 0. We're almost done. Now, since we are looking for the final speed, this is the final speed, angular speed. So we move everything else to the other hand side. So minus 1 over omega equals minus 80 minus 1 over omega 0. Now, it's better to make the left-hand side positive, so we will multiply both sides by minus 1. So 1 over omega equals minus times minus 80 is 80. Minus times minus 1 over omega 0, it's 1 over omega 0. Now, to add 80 plus 1 over omega 0, we should have the same denominator. So we unify the denominator by setting omega 0 at over omega 0 plus 1 over omega 0. What I did here, I just multiplied and divide with omega 0 in order to get the same denominator, which is equal to, now we have the same denominator, we can add them safely. Omega 0 is the same denominator here. But since we aren't looking for the angular speed, not the reciprocal of the angular speed, we flip this side upside down and this side upside down. So what is in the denominator becomes in the numerator and vice versa. So omega over 1, we don't need to write over 1. It will be the same. Equals omega 0 becomes in the numerator and omega 0 t or at plus 1 in the denominator. And this would be the final answer. And the final answer actually is A. Now, exercise 10. Two people, A and B, are riding a large horizontal rotating platform. The platform rotates around its center if person A is twice as far from the center as person B. So this is the center, let's call it I. And here we have person A and person B, because person A is twice far the distance as B. So which of the following statement is true? Now all the statements are describing the relationship between the angular speed and the tangential speed of person A and B. Now we know that during the motion, the disk will rotate. So A and B will start to move simultaneously. And at any point, they will be at the same line, placing on the same line or standing on the same line because there is no relative motion between the two people and the rotating disk. The disk, because of the rotation of the disk, the two people will rotate. So they will rotate covering the same angle, which means they will have the same angular velocity always and forever. So omega A is equal to omega B. Now, since here the radius is smaller than the radius there, and we know that the linear speed is related to the radius and the omega, since we have fixed A, omega, the bigger the radius or the larger the radius, the higher will be the linear speed. So we can say the V of A is much greater than the V of B. And another reason for that, the distance traveled here is bigger than or larger than the distance traveled there, which means both of them will have the same tangential speed, but person B or person A has a greater uh, tangential tangential speed. So both people have the same angular speed, sorry, same angular speed, but person A has greater tangential speed. So the correct answer would be C. Now, question 11. A solid disk of mass capital M radius R and rotational inertia I. We will talk about the rotational inertia in topic 5.4, I guess. And it's something related to the mass and the distance from the axis of rotation. So you can ignore it now. It won't affect the result. Is free to rotate about fixed frictionless axis that is perpendicular to the disk through its center, as shown above. A force of constant direction and constant magnitude is exerted on the disk. Remember that if we have applied a constant force, it means we will get a constant acceleration. In other words, we can use the kinematics equation to solve this problem. If the disk is moving clockwise with the angular speed, so we have the angular speed is 5 radian per second, and we have the alpha, which is 1.3 radian per second squared. What will be the angular speed after 3 seconds? So to find the angular speed, we just use one of the kinematics equations, and I will choose this one. Now omega is equal, the omega 0 is 5, the alpha is 1.3, and the time is 3 seconds. So the final answer would be 8.9 radian per second. It is with a diameter of 40 centimeter. Now, let me remind you between the relationship or with the relationship between the diameter and radius. We know that the radius is less than the diameter and it is exactly equal to the diameter over 2. So if the diameter 40 centimeter, then the radius will be 20 centimeter. Convert this into meter. We divide by 100 and the answer would be 0.2 meter. This is the radius. So the rotation, it's modeled according to this expression. Theta is equal 1 over 4 t to the power 4 minus 8t. And because theta is written in terms of a non-quadratic equation, then the type of motion here is non-uniform motion. However, in question A, they want me to derive an expression for the angular acceleration. They want me to find the alpha as a function of time. As I said, this is not quadratic equation. We know that theta should be written like this, something similar to this formula, theta 0 plus omega 0 t plus half at alpha t squared. So we have squared here, which allows us to use the kinematics equation. So here, we don't have access to the kinematic equation, and I will rely on derivative and integration, or in other words, the calculus to solve this problem, or to find the derivation of the angular acceleration. Now, let me remind you that theta, omega, and alpha are related to each other via the derivative. So the derivative of theta is omega, and the derivative of omega is alpha. So let's find out the omega first. So d theta over dt, we drop the power, we reduce the power by 1, it becomes power 3. minus the derivative of constant, it becomes linear. Sorry, the derivative of linear, it becomes constant. So 4 and 4 cancelled out, and the omega is t to the power 3 minus 8. Now to find alpha, we apply the derivative on the omega. We drop the power. We reduce the power by 1. It becomes 2 minus 8. The derivative of constant is 0. So the final answer is 3t squared. This is the expression of alpha. In part B, they want me to calculate the linear speed of a point on the outside edge of the disk after 4 seconds. Now, actually, to find the speed, let me remind you that the speed is given by r omega. And if we want to find the speed at particular time, after 4 seconds, I need the omega to be written or to be calculated at this time. So let's find the omega after 4 seconds, which means we're going to use the equation of omega or the expression of omega, which means we will need this one. This is the expression of omega. And we calculate the omega after 4 seconds by substituting 4 in every single t. We have only one place for t. So 4 to the power 3 minus 8. And the omega after 4 seconds equals to 56 radian per second. Now we use the formula of V equals R omega to find the velocity after 4 seconds. R is given by 0.2 and omega is given by 56. So the final answer is 11.2 meter per second. This is the linear speed. A flywheel with the diameter, again, we have the diameter, and usually we don't use the diameter in any one of our equation. We use always the radius, and the radius is related to the diameter by this relationship. The radius is equal diameter over 2. The diameter is equal 3.5 centimeter over 2. So 1.75 centimeter is the radius. Convert it into meter by dividing this number over 100, and the final answer would be 0.0175 meter is the radius. So this flywheel rotating 2,500 revolution per minute and comes to halt, which means to rest, in 1.5 seconds. So here it means the omega final is 0, the time is 1.5 seconds, and the omega 0 is 2,500 revolution per minute. However, we usually express omega or the angular velocity or the angular frequency in radian per second. To convert from revolution per second minute to radian per second, we simply multiply by 2 pi over 60, or we can just write pi over 30 after we simplify this fraction. So I'm going to use pi over 30 instead of 2 pi over 60. 2,500 multiplied by pi over 30, and the omega is 261.8 radian per second. Now question A. Calculate the magnitude of the tangential acceleration of a point on the surface of the flywheel. So on the surface of flywheel, the distance will be exactly equal to the radius. The distance between the center of the circle or the disk and the targeted point. We know that the tangential acceleration, it's directly related to the angular acceleration. So if we know the angular acceleration, then we can find the magnitude of the tangential acceleration. So let's find the alpha first. Now we have the omega 0, and the omega final, and the time. And we know that since the motion here is a uniform circular valid motion, then we can use the kinematic to solve the problem. And omega equals omega 0 plus alpha t. We move this omega is 0, omega 0 plus alpha t. We move omega 0 to the other hand side, so minus omega 0 equals alpha t, and the alpha is equal minus omega 0 over time. So minus, we don't use 2,500 revolution per minute. Instead of that, I will use the more convenient unit, which means the radian per second. So 261.8 over the time, and the time is given by 1.5 seconds. This is why the alpha is equal to minus 174.5 radian per second squared. We still need to find the tangential acceleration, and the tangential acceleration is equal to the radius, and we found the radius to be 0.0175 multiplied by minus 174.5 minus 3.05 uh, meter per second squared. This is the tangential acceleration. But since we are looking for the magnitude, we just drop the minus from our solution. And the magnitude of the tangential acceleration is 3.05 meter per second squared. Calculate how many revolutions the flywheel makes as it stops. So remember, in order to stop the flywheel, we will need to apply an angular acceleration during 1.5 seconds. Now we know that the number of revolutions is directly related to the delta theta. We know how to convert revolution into delta theta. We just multiply by 2 pi. So if we want to express delta theta in revolutions, we divide over 2 pi. So first we need to find the delta theta, and then we convert it into a number of revolutions. The delta theta here can be calculated using the kinematics equation. The type of motion here is uniform circular varied motion, and the best choice will be omega 0 t plus half alpha t squared. Now omega 0 is 261.8, the time is 1.5, plus half minus 174.5 multiplied by 1.5 squared. And the delta theta in radian is 196.38 radian. Now we convert this into revolution, which means we divide over 2 pi. So if we divide this value over 2 pi, so 196.38 over 2 pi, the answer would be 31.25 revolutions. So this is the final answer. A DVD rotates from rest, so the omega 0 is equal to 0, and to new omega, to final omega, which is 1500 revolution per second. So it's better to convert this into radian per second, and we can do that by multiplying this number with pi over 30. Because it's revolution over minutes. If it's revolution over seconds, we just multiply by 2 pi. But since it's combined with the minutes, then we multiply by 2 pi and divide over 60, which means we're going to multiply by pi over 30. And the omega here in this case is 50 pi. The 4 seconds is the time. Calculate the DVD's uniform angular acceleration. They want us to find the angular acceleration. We are assuming here that the type of motion is uniform circular varied motion, which means the alpha is constant, and we can rely on kinematics equation to solve the problem. And we will use omega is equal omega 0 plus alpha t. Omega final is given by 50 pi radian. Omega 0 is 0. We started from rest. The alpha is unknown, and the time should be placed here. So divide over time, which means divide over 4. And in this case, the alpha will be 12.5 pi radian per second squared. Now part B, calculate how many revolutions the DVD will make in 4 seconds. Now we know that the number of revolutions is related or linked to the delta theta. So if you find the delta theta, then we just divide over 2 pi to get it in revolutions. And the delta theta is equal, since we have the time, the alpha, the omega 0, we just use the quadratic equation to find the delta theta. Omega 0 is 0. So half alpha is 12.5, and the time is 4 to the power 2. So the delta theta is equal to 100 pi. Now in part C, calculate how far a point 5 centimeter from the center. So we have a point that is located 5 centimeter from the center. So here the R represent the 5 centimeter. How much or how far it travels during 4 seconds. So we are looking for the distance. We know that the distance is related to delta theta via this equation, where R, the distance, the radial distance between the center of the rotation and the targeted point. And R here is, in this case, is 5 centimeter. We should convert it into meter. We divide over 100, so it's going to be 0.05. And the delta theta is 100 pi. So the final answer will be 5 pi. This is distance, so the unit will be meter. Now, the last question in this lesson. A fan blade rotates with angular velocity given by omega is equal to 3 minus 0.7 t squared. In part A, they want us to find an expression for the angular acceleration. Let me remind you that the derivative of theta will give us the angular velocity, and the derivative of the angular velocity is the angular acceleration. Now, since we have the angular velocity, it's enough to apply the derivative only one time. So alpha is equal to omega over dt. The derivative of constant is 0, and the derivative of the second term, we just simply drop the power and reduce the power by 1. So it becomes minus 1.40. This is alpha. In part B, calculate the instantaneous angular acceleration. So they want me to find the angular acceleration at specific time. We just need to substitute the time in the alpha expression. Alpha at t is equal to seconds equals minus 1.4 multiplied by 2. And the final answer is 2.8 radian per second squared. This is alpha. Now, in case they want me to find the magnitude of the instantaneous angular acceleration, we just need to drop the minus from our answer. So the alpha becomes equal to 2.8 radian per second squared. And that's it for today's lesson on 5.1 rotational kinematics. Thank you for joining me. See you next time.